The total revenue test works like this. When elasticity, which is denoted by this fancy looking E, is between 0 and 1, meaning that your price is inelastic, an increase in price will raise total revenue. When elasticity is greater than 1, so your price is elastic, an increase in price will lower total revenue. And in between those two, when elasticity is equal to 1, total revenue is maximized. So let's see how this works. As I said earlier, revenue is equal to price times quantity. When your price is inelastic, that means that increasing the price will still be met with a decrease in quantity demanded, but the increase in price will be greater than it. So we can show a large increase in price and a small decrease in quantity. When these two numbers are multiplied together, the increase in price is greater than the decrease in quantity, so revenue, or total revenue, will increase. With an elastic demand, it's just the opposite. For even a small increase in price, we'll see a large decrease in revenue. A large decrease in quantity demanded, which means that our revenue will decrease. And for unit elastic, when elasticity is equal to 1, that means that the increase in price is perfectly matched by the decrease in quantity. So this product, which is equal to revenue, remains the same. So let's show this on a graph. When your price, we have price on the x-axis and total revenue on the y-axis. A change in price determines a change in total revenue. So this makes sense. When your price is $0, no matter how many you send, you're not making any revenue. So you can put this little dot here. And eventually, if you raise your price high enough, you're not going to sell any. And so we can put another dot over here. If you sell a pair of shoes for $10 billion, nobody's going to buy them. And you won't make any money from them. And then in between, we see that even a small increase in price will have a relatively large effect on the total revenue. And eventually, this is just a rough sketch, mind. We'll go up, max out, and come back down. So from here, when we're inelastic, an increase in price increases total revenue. That's the left half of this curve. I for inelastic. On the right side, we're still increasing price, but our total revenue is going back down. That's an E for elastic. And then in between, this very top here, a single point, is where we are unit elastic. And so if firms are trying to maximize revenues, they find the point where they are unit elastic. As I said, the previous graph was just a sketch, so I'll show it to you with some real numbers. Here we have a table of prices and quantities demanded for socks. When the price is $0, 8 pairs are demanded. And then from then on, for every increase in 50 cents for the pair of socks, 1 fewer is demanded. And so we increase to $4, and nobody wants to buy socks that are $4. We said earlier that revenue is equal to price times quantity. So we can easily fill out the last column of the table. 0 times 8 is 0, and then 3.5, 6, 7.5, 8, and then back down symmetrically. In this case. It won't always be the case that it'll go back down symmetrically, but in this case it is. 6, 3.5, and 0. So now, instead of graphing price versus quantity demanded, which is what you do to get your demand curve, it would look something like this. With price here, quantity here. When price is $4, 0 are demanded, and when price is $0, 8 are demanded. This would be your demand curve for socks. But we're not interested in that right now. We're going to look at the application of elasticity here. So we're going to graph price on the x-axis versus revenue on the y-axis. When price is $0, total revenue is also 0. And then when price is 0.5, we move up to 3.5. That's a huge change for just 50 cents. The next 50 cents brings us up to $6, which is shown approximately right here. The next change in 50 cents brings us up to 7.5. At $2, we go up to 8, and then, as on the table, back down symmetrically. 3.5 and 0. So now, if we connect the dots, which we would do assuming that you can buy fractional portions of stocks, or if this were a larger scale, if these were thousands of stocks, we could have 7.0001, or maybe not quite that many, but we could have everything in between, and so it is useful to connect the graph. And so you'll see that this looks just like this. It's a quadratic equation that opens downward. So we can do the same thing we did before. We can divide it in half. This portion will be inelastic. This portion will be elastic. And right here, we're unit elastic. So when price is $2, the revenue is maximized. And so from this graph, without doing any calculations, we can tell that right here will be unit elastic. If you want to verify that on your own, you can try going into this table and try moving the price from $2 to $2.50, which means that your quantity demanded will decrease from 3 to 2. And this will show, assuming that I did my math correctly, this will show that the elasticity is 1 at this point, so we're unit elastic. And so businesses can use elasticity to determine whether they should increase or decrease their price to maximize revenue. However, businesses try to maximize profit and not necessarily revenue. Sometimes increasing revenue, for example, if you're in this section, increasing revenue means you're producing more. Or the other way around. When you're over here and price is high, you're not producing very many. So increasing revenue increases the number you have to produce, which means the cost also increases. So where maximum profits are is not necessarily where maximum revenue is. And finally, the market sets the price, and so the businesses can't always decide where it should be. So, like with many things you learn in economics, there is a theory, and it's useful mathematically and in explaining, by and large, what happens. But it's not always what happens in reality.